business math. All right, so you got your test back. It wasn't a good test. I wouldn't go that far, but I also know that historically, it's just usually not a good test for anyone, okay? So if you did well, congratulations, great. You've got it under your belt, but I just have to change this here so that I can't do two things at once, I guess. There we go. This is time for me to reiterate my policy of if you do better on the final, right, I'll take the weight of this test and put it on the final exam, okay? So if you got a score and you think you can do better on the final exam, then who cares about this test, right? It'll be like it never happened, right? And so I think that's pretty fair, right? And on the plus side, what we're gonna start doing today and kind of moving forward is gonna be, well, it's gonna be different from what we have been doing, but also kind of more methodical, right? We start with simple interest and then move into compound interest and then annuities, but there's gonna be kind of a continuous flow of kind of concepts, not this all jumping around and linear, we gotta do linear programming and then we have to do derivatives and then we have to do this and that and whatever, right? So this stuff is gonna feel very different. And for that reason, if you're thinking, oh man, I failed this test and I have to drop the course, which I overheard some over here. No, it didn't work out that way, right? But even if that was the case, if you're feeling like, oh man, this is brutal, just stay on it, okay? Test 2, test 3 are gonna be very different, right? Same idea, right? But different materials, okay? And so I guess don't worry about it. Just do better on the final, okay? So I don't want this to bring you down or bog you down in any way, okay? No idea. I don't usually care. I get a pretty good idea of how the class did. And to be quite honest, you did better than I thought you would. So that's pretty good. That's nice, right? Hey, what's she actually saying there? I don't know. Okay, so because you haven't gotten any marking back from me before, there are a couple of things that I want to talk about before we get started here. Okay. But just for marking, first of all, you'll start at 100%, and then I dock you marks as you make errors. Okay, so, or if you don't write anything, there's nothing for me to, I can't do anything with that. Oh. Hey, Kev, it's actually showing on the screen, but I'll get back to you later. Sorry, hope you feel better. Anyways, okay, so y'all start at 100%, and then I dock you marks. I think that that's a kinder way of grading than for you to have to build up marks, right? Because there's often things that we think about in different ways. And so if I'm looking for something in particular, then it just makes it hard to mark. So I've tried my best to follow through with your logic and reasoning, right? And so even if something goes wrong at the beginning of a question, if you follow through with that number, right, how are you supposed to know that it's wrong? That's kind of my, I don't know how you would know that, right? So as long as you follow through and with the same logic and reasoning, then you're pretty safe, okay? So for marking, one thing I write a lot is okay. It's usually like a little scribble. Okay. So okay can mean a lot of things, and if you're wondering what it means in your case, it can be something like, okay, or like, oh, okay, or okay. So usually it's like you followed through and hello, hey, in the back, thanks. Right, so you followed through, and even if you did something wrong in the beginning, right, you followed through and everything's okay, right? Or if you're not quite there, but there's not enough to take marks off, right, then I write an okay just to, so the okays are there to alert you that it's not actually right, but so you have to look into it, right? But not worth taking marks off for whatever reason, right? Oh, I get a lot of questions about -1/2 is always just -1/2 a mark. It's never -1 out of 2 marks. It could make a difference, right? And so -1/2 just is always going to be just a half mark off. Okay? So that can be confusing. I wrote, be careful a lot, right? So if you're just kind of bouncing around and maybe missing some things, like a minus turns into a plus, or vice versa, or just something where you're just on the page, it looks like you were rushing, right? Or just not quite thinking things through, then I say be careful. I also said things like, reasoning or logic, right? Because what I was finding was you were just putting down everything in the formula already, right? But what I would want to see is I want to see the formula that you're about to use and then put stuff in and then go through and follow through, right? And so, and that shows me your thought process better than, oh, okay, and then over here, and then over here, and then over here. And I know it's a test, so you know, you're thinking of things as you go, but yeah, I think it'll pay off if you just kind of start with your empty formula, fill it in, and go from there. Okay. All right. Any other comments on there that you're not quite sure about? No? Nothing. All right. Okay. And I don't know the average. I never, by the time I'm done entering grades, I'm like, oh, done. I'm over it. Oh, and I should say your guys's were marked on the plane, so the writing was probably a little bit subpar. It's like, but anyways, I got it done, didn't I? So, oh, let's put test 1 behind us. Sounds good. Let's start with part 3. Who knew the textbook had parts? It does. Part 3. We haven't paid attention to them till now. But so part 3 is on simple and compound interest. Okay. But much like before, we're going to start in section 4.1, which is vaguely called the basics. Okay. So today we're going to go through and we're going to talk about how do we handle exponents, so laws concerning exponents, and how do we deal with logs, so logarithms. Okay. And so we'll kind of work through that. And as you probably noticed with this course already, there's going to be kind of a day where I introduce all this stuff and then we move on, and I just assume that you know this from now on, right? And so there is a lot of stuff that we're covering today, but from now on, I'll expect you to know how to deal with exponents and logs, right? So, yikes. So we'll start with exponents. Or powers, if you want to call them that. Okay. So, what are they? If we have something like a times a times a times a times dun 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 n times. You can rewrite this as a to the power of n. Right, so this should be kind of a familiar concept, but we'll go through. So here we have n a's multiplied together. Here, we call a the base, so whatever's in the bottom, we call it the base, and n is the power or the exponent. Okay. So here, a is the base, and n is the power or exponent. I use those interchangeably. And you can too. Not just for me. Okay. So really, all we're saying again is just a to the power of n is a multiplied, or I should say is n a's. No, I'll rephrase it from what we just said. Sorry, starting where I was before. A to the power of n is a multiplied by itself n times. If you have something like 5 times 5 times 5 times 5, 5 is your base, right? And it's being multiplied 1, 2, 3, 4 times. Or if I had to write out 2 to the power of 5, right now 2 is the base and we need it 5 times. 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5. Phew. 5's too many. So we've already actually seen exponents and we've combined bases before, but now we're going to talk about the actual rules of exponents. Okay. So the rules of exponents. This is on page 92 in your textbook, but what you'll find is, even though they're all there, the rules, it's probably in pretty foreign math speak. Once you've done enough math, you kind of become blind to it. And so I think that's, it's probably not obvious looking at what's on these pages and going, oh yeah, I know what all those are saying. Right, so we're gonna write them out and then I'm gonna write little notes about what they're saying as best as I can. Sometimes it's easiest to just show the math, but I'm gonna try to explain them as best as I can. So some ground rules, okay, is that the base has to be a positive non-zero value, okay? So when we say something let a be greater than 0, we're saying that the base, okay, must be a non-zero positive number. M and N are in the set. If you know kind of set notation, are in the set. So it's a round E, kind of like a euro, I think. of real numbers. And this is kind of the main reason why I really wanted to write these out, because I don't think that you've seen this notation before. Maybe in calculus. Yeah, it's a fancy R with 2 backbones, I guess you'd call them. Okay, so really what it's saying is that we read this as M and N are in the set of real numbers. Okay. What's the set of real numbers? The set of real numbers are all the numbers that we can think of, right? From negative infinity to positive infinity. Okay. And so that's why it's kind of a given, but when you see it like this, it's like, well, how am I supposed to know what that means, right? And so the set of real numbers, is any number between negative infinity and positive infinity. So just any number. So those are the rules that we're playing by. And so here, the first thing, and we already said this, was a to the power of n is just a times a times a times a. A multiplied n times. Oh. Phew, we've got that one down already. Great. Here's the one that we kind of covered already. Well, we used it briefly. A to the power of n times m times a to the power of n. We can rewrite it as a to the power of m plus n. So if you have the same base being multiplied together, then you can combine them by adding the powers. Okay. So if we have the same base multiplied together, we can combine them. We can combine them by adding the powers. What we'll see is we'll start probably just working from left to right, but works the other way too, right? If you have something that you can break up into a to the power of m plus n, right, then you can rewrite it as a to the power of m times a to the power of n, right? And that's sometimes nice for pulling out common multiples, for example. So we've seen that one, sort of. If you have a to the power of m over a to the power of n, same idea. We can rewrite this as a to the power of m minus n. Right, so multiplication, we add the powers. Division, we subtract the bottom power from the top power. If dividing powers of the same base, we can simplify by subtracting the exponents. So far, so good. So if we have something like a to the power of m to the power of n, you can simplify this as just a to the power of m times n. Right? You can just bring that power inside. This is really just an extension of rule number 1, right? Because if we imagine a to the power of m as the base, right, we can just imagine that, okay, well, now this is our base, not just a, right? Then we would have a to the power of m times a to the power of m times a to the power of m times a to the power of m n times, right? And then each of those a to the power of m's would turn into a times a times a times a m times. Yikes, right? But it's the same as a to the power of m.
You don't solve for am and then add that to n?
Depending on the problem, you can. Yeah, it totally depends on the situation. So this is just an extension of rule number 1. Kind of going hand in hand with a times b all to the power of m is the same as a to the power of m times b to the power of m. So what we'll find is as long as we're multiplying or dividing, is the next rule, inside, right, as our base, then we can bring that power onto each of the items inside. Terms. Okay. So if multiplying two bases the power expands inside, so expanding meaning removing the brackets, right? The power expands inside onto both bases. Or 3 or 4, as long as they're being multiplied or divided together, then you're fine. So like I said, if you have a divided by b all to the power of m, we're dividing, so it's safe, like I said. Then we can rewrite this as a to the power of m over b to the power of m. Often, we won't want to go from here to here. We'll probably want to recognize that, oh, I have the same power here and the same power here. I can rewrite it just simpler like this, right? Pull that power outside, right? But yeah, probably a 50-50 usage, right? Pulling it in, pulling the power out. Pulling the power out? Nice. Yeah. So this is just an extension of rule number 5.
For number 5, is it the same? Like which one will be the simplified term of this one?
About equivalent. Yeah, it depends. It just depends on which way your math is going that you'll want to. Yeah, so simplified. Yeah, I'd probably say the first one, a b to the power of m, might be simplified. 3 things instead of 4, but that's about it. Excluding the brackets, so. But yeah, good question though. About the same. So, does, yeah. Yeah, you'll get the same answer whether you solve inside the brackets and then do the power, right? Or if you expand and then do it. Okay. We've already seen this one, a to the power of 0, so anything to the power of 0 is 1. Weird, right? 0 times anything is 0. Something to the power of 0 is 1. Okay. That's just a fact. Okay. Here's a sneaky trick that we'll use. A to the power of negative n is the same as 1 over a to the n. Right, so when you have a negative power, you just bring all that down to the denominator, right? And so that's handy, right? If you have something down here in the bottom and you want to bring it up to just the same level as everything else, then you can just make the power negative and bring it up, right? And so I'd say we use that more, where we take something from the bottom and bring it up by making the power negative. Okay. But like I said, we have to be flexible in how we move across these. A base with a negative power can be written, oops, getting sloppy here, can be written as a fraction with the base and positive power in the denominator. That's cool. Okay. I remember using this one in high school, so you've probably seen it maybe. A to the power of 1 over n is the same as the nth root of a. Right? If you have to take the 15th root of something, how would you do it? So the 15th root of 3, for example, you do 3 to the power of 1 over 15. Right? And so working from right to left, right, that's how we translate something to work in our calculator, right? The 1 over whatever root we need, right? And so we write the nth root in the little hook here. Okay. We're familiar with the square root, right? Technically there's a 2 there, but we don't usually write it, right? But any other root that we need, 3rd root, 4th root, 500th root, right, you would write the number in the hook. Okay. So we can rewrite the nth root as a power I'll just leave it at that. It's one of those cases where the math shows it better than I can write it. Yeah. Do you mean, and so if you have something like the 3rd root of 4, right, that's the same as 4 to the power of 1 over 3. 2 over 3? Oh, Oh, funny you should ask. That's my next point. So if you have something like a to the m over n, yeah? Okay, let's break it down then. Well, I can rewrite this as a to the power of m times 1 over n, right? So we'll start there. A to the power of m times 1 over n. That's just a fact. M over n, I can rewrite it as one thing being multiplied by the fraction. Okay. So then I can rewrite this, right, as a to the m and bring the 1 over n outside. Can't remember what fact that was, right? But fact 4. Oh, what happened here? Oh, 1 over n. So now a to the m to the power of 1 over n, that's the same as this rule, right? Just treating the a to the m as the base now. Now we have a to the m inside the nth root. So we have the same as the nth root of a to the power of m. It does. Yeah. Yeah, so the numerator is going to stay with the base, and the denominator is going to be the root. I don't really have a word explanation of what we just did there, but it's kind of, that's the end of the rules, as hard as it's going to get for exponents.
So with the tree root for your above, that means that what answer that would be what number times by itself 3 times before?
So what, yeah, so 4 multiplied by itself a third of the time. It doesn't really make sense, right? But that's moving into the roots, right? It's more a trick for putting it into your calculator than to think about, because 4 multiplied by itself a third times doesn't make sense.
The root of 9 is 3, so the third root of 9 would be.
I don't know.
Not just 3 times by itself, it would be what times by itself 3 times equal 9. Yeah, exactly. So it's not just 3, it's more times itself 3 times. You would take the cube root of 27. All the times 3. Sounds good. Okay.
But kind of tricky to wrap your head around, I think. So I wouldn't worry too much about it. As long as you know how to rewrite these roots as a power, or vice versa, then you're good. Right. Cool. So let's do a little example, example 117. Simplify something like a to the 4 times a to the 8 over a to the 7. Oof. That's okay. I'll just rewrite it here. A to the 4 times a to the 8 over a to the 7. What I prefer to do, there's lots of ways that we could tackle this, right? As long as you get a to the power of 1 number at the end, you did it, okay? As long as we get to the same number, right? I like to bring the denominator up to the numerator so that I'm working on the same playing field, right? I just find that that's easier than simplifying the top and then the bottom and whatever. But it's really just going to be whatever looks the easiest. Okay? So I'm going to do a to the power of 4 times a to the power of 8 times a to the power of negative 7. Right? To bring it up to the top, I just make a negative. Right? So those are equivalent. Yeah. And I just want to make sure that I have the same base. If I have the same base, right, then I can combine them by adding all the powers, right? So this is the same as a to the power of 4 plus 8, technically plus negative 7. If you went straight to minus 7, that's fine. Okay, but technically plus minus 7. Which is going to be, I'll put it here. A to the power of 4 plus 8 is 12 minus 7. Let's say 5. Okay.
So to bring the denominator up, you just make the exponent negative?
That's right. Mm-hmm. And vice versa, if you had to bring it down, right, you could bring a negative exponent down. But then you'd have to ditch the negative.
I mean, yeah.
I think so, if I'm following.
Yeah, but if you brought it.
Great. Okay, so as long as you got a to the power of 5 at the end, then you did it right. Okay. What if we had to simplify? So example 118. Simplify something like 1 plus I to the 3 times 1 plus I to the 9 over 1 plus I to the 6th. It might be tempting, right, to just pull in these powers, collect like terms, and be done with it. But that would be illegal math. I saw quite a bit of illegal math on this test. So you'll want to nip that in the bud, right? And make sure you don't keep doing it. Okay. So illegal math, because we're adding or subtracting inside here, we can't actually bring in the powers. That's only true if we're multiplying or dividing inside, right? So I think of multiplying and dividing, they're best buds, and adding and subtracting, they're best buds, right? So that's how I keep track of them. Okay. And I think we all think that way. Okay. So if we had to simplify this, we are going to treat the 1 plus I as just the base, right? So we just treat it as one number, but just to emphasize why just bringing in the 3 is illegal math, I'm going to show you why. Okay. So here's a note. We can't say 1 plus I to the power of 3 is 1 to the 3 plus I to the 3. We can't. Because if you have 1 plus I to the power of 3, what does that mean in terms of exponents? It means that you have 1 plus I times 1 plus I times 1 plus I. So now we're going to FOIL this out, starting with the first 2, leaving the last set of brackets, right? And so this becomes 1 times 1 is 1, plus 1 times I is I, plus 1 times, or I times 1 is I, plus I times I is I squared, all times 1 plus I. Oof. Okay. FOIL this again. 1 times 1 is 1. 1 times I is I times 1 is I times I is I squared. How many did I do? I times 1 is I times I is I squared, plus I squared times 1 is I squared, plus I squared times I is I to the 3. Yikes. It's actually easier when I don't have to say it out loud, when I can just. But in the end, we get 1 plus 1, 2, 3i plus 1, 2, 3i squared plus I to the 3. Okay. Since 1 plus I to the power of 3 is 1 plus 3i plus 3i squared plus I to the 3, saying 1 plus I to the power of 3 equals 1 to the 3 plus I to the 3 is illegal math. Everyone convinced? It's illegal math. I don't want to see it. I will see it, but hopefully you'll remember this day when I say illegal math. How about this? If I knew how to draw a skull and bones, I would. The poison sign. Okay, so that's just to convince you. Okay, so if we have to simplify, 1 plus I to the power of 3 times 1 plus I to the power of 9 over 1 plus I to the power of 6, right? I'm going to use the same method as before, where I take the denominator and I bring it upstairs, right? And so I get, hopefully I have some room here, 1 plus I to the 3 times 1 plus I to the 9 times 1 plus I to the negative 6. Right. And then I have 3 plus 9 minus 6, 1 plus I to the 6, right? Oh, I guess I should have shown some work there. Got carried away. And in the future, it is okay to just go from there to 6, but I'll do 1 plus I, 3 plus 9 plus negative 6 is 1 plus I to the 6. Got carried away. Questions, comments, concerns? Yes?
Would you want us to expand past that, or just?
Nah, that's good. Yeah. Because that would just get nasty, I think. Or I know. Yeah, so that's fine. If I asked you to simplify, bracket, x plus 3, right? So we can't bring the power in, to the power of 5, and then to the power of 3 over 2. Okay. I'll just rewrite it here so I can work with it. Bracket, x plus 3 to the power of 5 to the power of 3 over 2. First, we can expand into these brackets, right? So remove these brackets by just saying, well, that's the same as 5 times 3 divided by 2. Right? Multiplying fractions we talked about, right? You just multiply across. So they're fun to deal with. This is going to be the same as x plus 3 to the power of 5 times 3 over 2. I'll just say rule number 4 here. You don't have to, it's just so if you're looking back then, because this one's a little bit harder than what we've been dealing with so far. So then we can just simplify the fractions, right? 5 over 1 times 3 over 2. So we have x plus 3 to the power of 15 over 2. So now we have that same situation that we saw, right, where we have the square root of x plus 3 to the power of 15, right? The numerator stays with the base and goes under the square root. And the 2, well, that's what makes the square root, right? The over 2. So this becomes the square root of x plus 3 to the power of 15. We have to keep those brackets on, right, to the power of 15, as we just saw. Right. And then that's simplified. So this is rule number 10. It's technically here the square root. For the square root, we don't put the 2. Yeah. All the other roots we specify. Nice. Okay. So when do we need square roots or roots in general? Right. So we use roots to undo powers, right? Just like subtracting undoes addition, division undoes multiplication, right? I think of those kind of, they go hand in hand, right? And so now roots undo powers. Right? So we use roots. We use roots to undo powers. So for example, solve x to the power of 5 equals 4 for x. So you know x to the power of 5 is 4, but you want to just know what x is, right? And so you want to get x on its own, but how you're going to shake out that power is you're going to take the 5th root of both sides. Right? And so you have x to the power of 5 is 4, so just starting with the original. And then we're going to take the 5th root of both sides. So let's think about what happened.
Is that better, Kev?
Yeah.
Yeah. You can send a cool face emoji next time. Great. Thanks for that. Okay. So now I'm going to do a bracket and then 1 and then divided by and then 5 and then end bracket. It's a lot when you write it out like that. But really on here, it's not that bad. 1 divided by 5, end bracket. Once you end the bracket, it'll say 0.2, right? That's 1/5 though. So you have to finish it with the equal sign. Otherwise, it won't do it. So you should get x is equal to 1.31950791. And I'm only doing all those decimal places. Well, 1, because it's a hang up of mine. Once I get writing, I don't stop. But also so that you can make sure that you're getting the right answer on your calculator. There shouldn't be anyone who's still just having 2 decimal places on there. But if you are just getting 2 decimal places, you need to come see me later, not now. Okay, great. Well, because I want to solve for x, right? And so to shape the 5th power, yeah, I have to take the 5th root. But whatever I do to one side, I have to do to both sides. Yeah. And then, I mean, technically, here you're done. But if I want an actual number, right, if I said to 5 decimal places, for example, then you'd have to use your calculator and do this to this, right? Cool. Any other questions? All right. What if I asked you something? Example 121. Solve x times y squared equals x squared minus y squared for y. We could solve for x, but I'm asking you to solve for y. All right. So it's going to take some finagling, right? We know we want to get y on its own, right? And so we start migrating all our y's together and everything else that we can shake out on the other side, right? Doesn't matter which side you pick, but I'm going to rewrite this out here in the middle of my page because I've got an equal sign, so I'll just write it like this. xy squared is x squared minus y squared. Okay. I'm going to move my y's to one side, so I'm going to move them to the left-hand side. So I get xy squared plus y squared is x squared. Move y's to one side. What's the next thing I want to do? I'm trying to get these y's on their own, right? I've got a common multiple of y squared, right? So I'm going to pull that common multiple out. So I get y squared times x plus 1, right? If you expand that y squared back in, you get y squared times x plus y squared. That's the same, right? So we've pulled out that y squared, and nothing happened on the right-hand side yet. Okay. So here, pull out common y squared. Sure can. Because if you, well, I guess from this way, right? Or if you multiply this back in here.
if ever I'm doing kind of factoring where I'm not sure, so factoring is when we pull out these things, right, the common multiples. If ever I'm doing something and I'm not quite sure it worked, right, I did it right, then I'll just quickly put it back in and make sure that I get to the same thing that I started with, right? Otherwise I need to backtrack. So here, right, if I pull this back in and I say y squared times x, right, that's the same as xy squared. Y squared times 1, that's y squared. So we'll be doing that quite a bit. All right. Now that we've got y squared times x plus 1, right, now we can divide both sides by x plus 1 to get y squared on its own. So now we can get y squared is x squared over x plus 1. Divide both sides by x plus 1. Clean up this x here. So now I know that y squared is x squared over x plus 1. Fine. But I want to solve for y, not y squared, right? And so I'm going to take the square root of both sides. So the square root of y squared is the square root of x squared over x plus 1. Take square root of both sides. Because we know that that's going to dissolve the square, the power of 2, right, on the y. Right, but now we have to deal with this square root over x squared over x plus 1. Yikes. I wouldn't be doing my job if I didn't throw on the plus minus. I don't want you to be concerned with it. I won't take marks off if you forget to do it. It's just the problem is when we square something, squared values are all positive, right? And so we lose that negative. And so when we take the square root, we have to open up to the possibility of the answer being potentially negative. We don't know. And so, oh man. Okay. So that's why I have to put the plus minus there, because technically that's what it is. But if you just ignore this or don't put it at all, I don't care for this course. It's good to know in general if it ever comes up. But for this course, I really don't think that we'll need it. If it becomes important, I'll let you know. Okay. So now we have y is the plus minus square root of x squared over x plus 1. You don't have to keep the brackets in the bottom there, but I am, just because I know what I have to do next. What's the next thing that I have to do? I'm gonna try to get rid of the square root by rewriting it as a power of a fraction, right? So then I get y is plus minus, and then in brackets, right, we have x squared over x plus 1, all to the power of 1/2. Right. I'm just rewriting that square root as a power of 1/2. Okay. Now I can bring in that power, because inside here, right, and that's why I kept these brackets on here, because if I look at this, well, this divided by this, as long as I'm putting this power on this whole thing, x plus 1,
then it's safe, right? We can only bring it in if we're multiplying or dividing in there, right? But as long as we're treating the x plus 1 as one thing, right, then I can bring this power in on both the numerator and the denominator, which is nice. So then we get y is the plus minus of x to the power of 2 times 1 over 2 over x plus 1 to the 1 over 2. So then y must be equal to, so x to the power of 2 times 1 over 2, that's just 2 over 2. So that's just going to be x. And to make it look a little bit nicer, right, the x plus 1 to the power of 1 over 2, I'm just going to rewrite as x plus 1 square rooted. But if you left it as 1 over 2, that's fine. Okay. Another way that we could have done this is, because it behaves the same way, right, is we could have said, well, this square root, if we're multiplying or dividing inside, not adding or subtracting, it doesn't work for that, right? I can just say that that's the same as the square root of this over the square root of this, right? And that's exactly what we did here, right? We took the square root of this over the square root of this, right? So the square root splits up over the numerator and denominator as long as we're just multiplying and dividing in there. Okay. Cool. This is simplified. We did it. How do you know? You just kind of keep going until you can't do anything else. Okay. Let's talk logs. Okay. But first, what if I wanted you to solve 7 to the power of x for x? That's tough. When we have x in the power, we need to be able to deal with that. So what if we have to solve, it's easier to think of equations, 7 to the power of x equals 2 for x. When x is in the power, right, it's hard to get at. So in come logarithms. And it's so funny with logs because we just call them logs, right? Logarithms is hard to say. But whenever, so I was doing my undergrad, I think, in math. And so my grandpa, he was like, oh, so logarithms and stuff. He's like, okay, I understand what you're doing there. And I was like, yeah, sure. But they're just like this little side thing. We just use our calculator, no big deal, right? But then I did the history of math, whatever. And turns out they were a big deal. So very computationally extensive in computing logs. And now we just push a button and it's done, right? And so he was like, oh yeah, like logarithms and stuff. I was like, yeah, sure. So something to brag to your grandparents about, I guess. I don't know. So logs are what we use if we want to solve for something in the power. Okay. So if we need to solve for a value in the exponent, right, or the power, we will need
to use logarithms. Can't remember what, we do logs in high school now, but I'm pretty sure, unless something's changed in the unknown amount of years. But I think we do. Help me out here, guys. You've seen logs? Yes or no? See it all the time. Yeah. Okay, fair enough, fair enough. So logs can have any base, and we're not going to talk about the bases or what it does to the math behind it, but we're going to use the natural logarithm. So the only log that we're going to use is the natural logarithm, which is log base e. E itself is a number, 2.71828, whatever. It's like pi, but different. It's a different number, 2.7. Okay. So here's a little note. Logs can have any base. Okay. The most common bases are base 10 and base e. E is roughly 2.71828, blah, 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 blah. We will work exclusively with log base e. We will work exclusively in log base e. Which we can write log sub e, but we won't. It's also called the natural logarithm. Also called the natural logarithm. Denoted by lowercase l, lowercase n, or when I write it, just looks like ln scribbles. So when I say log, what I mean is the natural logarithm, log base e, but I'm just going to call it a log from now on. I think most fields will be using the natural logarithm as its log. Okay. Might have called it ln back in high school, maybe, ln, ln, but I'll just call it log. Okay. So we're gonna, just like we did with exponents, we're gonna develop some of these log laws. Fun to say, fun to do. Okay. So we're gonna develop these log laws, and just like the exponents, right, I'm expecting you to be comfortable working around in them from today forward. Okay. So if it's not clear, then we need to do some work on that over the weekend. We don't, you don't, you do. I know them. So all of the log laws we develop here apply to any base, as if you care, but we will only show ln, log. Log laws. Here we go. So kind of familiar setup. We're going to have A and B have to be in the set of real numbers, but they have to be positive. So how we're going to read this is A and B must be positive. Fair enough.
This also on page 19?
No, it'd be a little bit later. Let me find it because that's good. 96. Okay. So A and B have to be positive. Okay. And the first rule, and the one that we'll kind of cling to with our lives, is that we can rewrite something like log of A to the power of B is equivalent to B times the log of A. You can see why this is so handy, right? Because if we're trying to solve for something in the power, and we can take the log of it, then we just bring this power down in front, and now it's on the same playing field that we can actually work with, right? We can't do anything in the powers, right? Because they behave differently than our regular kind of numbers, right? And so this is really handy that we can just bring down a power, right? As long as we take the log of both sides, right? Then that allows us to bring down the power, but then we have to deal with these logs. But at least we brought the power down. Okay. I don't have any notes about this one. I think it's pretty, what can I write here? Can't think of anything. Bring the power down by taking the log. That's what it says. Right? Thanks. Good. Can't think of anything else to write. Same idea here, log of A to the negative B. Well, you have to bring the whole negative B in front, right? So you get negative B times the log of A. A to the negative B is the same as what? 1 over A to the B, right? So that's something to keep in mind. Note that A to the negative B is the same as 1 over A to the B. That's from Exponents. If you have something like log of A times B, you can rewrite this as the log of A plus the log of B. And all of these, right, we can move from one way or another, and it's just to make your life easier, right? When you're trying to simplify things and solve for things, right? If you have something, if you have a bunch of logs added together, right? Log A plus log B plus log C plus log D, it might be easier to just say, well, that's the same as the log of A times B times C times D instead of taking the log of each of them individually, right, for example. So, same idea, similar idea. The log of A over B is the same as the log of A minus the log of B. So let's actually solve the one we started with. 7 to the power of x equals 2. Solve 7 to the power of x equals 2 for x. Okay. Rewriting it here, 7 to the power of x equals 2. I know I have to bring the x down, right, from the power, and so I'm going to take the log of both sides. So I get the log of 7. I skipped a step, sort of. I'll be careful. The log of 7 to the power of x is the log of 2. We have to remember to do it to both sides. The log of 7 to the power of x is x times the log of 7, which is the log of 2. Okay. I wanted to, or I did, just go from here to here, and that's okay. Okay, we'll get to that, right? But I figured I should jump in, show this intermediate step. But if you just go from the first layer to the second layer, I'm just ripping through battery here. That's okay. Oh, you guys were so hopeful, I'm sure. Sometimes I like the pressure of the battery. I don't know. Okay. So from here, right, we want to get x on its own. X is being multiplied by the log of 7, right? And so we can say the same thing. So x is the log of 2 divided by the log of 7. For some reason, when it's charging, you guys are in luck. The pen doesn't write as good. Weird, right? Watch this. I don't know what happened. It's when it's charging, it doesn't like that. So I'm still on the 5% crunch. Okay. How do you take the log of 2 on your calculator? So the log of 2, where do I want to take this? Here. Log of 2 on your calculator. You're going to put 2 on the screen. This one's easier. And then hit the LN button. It's a capital L, capital N. You've got your clear down in your lower left-hand corner, and then your recall, and then your store, and then your log button, or LN. And then, even though you won't need it because that's all we did, it's good to just get in the habit of always pressing the equal sign when you're done, right? Because sometimes it shows those intermediate calculations, and you want to finish with the equal sign. Okay. So we get 0.693147181. Okay. How are you going to do the log of 2 divided by the log of 7 on your calculator? Same thing. We can just do a string of calculations. So 2 ln divided by, and then 7 ln. It's going to show you, this is where I want you to be careful, right? It's going to show you that the log of 7 is 1.94591, blah, 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 right? But we have to hit equals now to get 0.356207187. So just make sure that you're getting the same thing that I am. So now I can just say that x is 0.356207187. Kind of side note, back up. Okay. Any questions about that one, or is it all working out? You're trying it. Cool. Cool, cool. What if I asked you to solve f is equal to p times 1 plus I to the power of n for n, without knowing what f or p or I or even n mean? We can still manipulate these to solve for n. Okay. So I'm going to rewrite this here. F is p times 1 plus I to the power of n. I want to try to get just a clear, right? So I want to get this n as simplified as possible. So for that reason, I'm going to divide both sides by p, right? Bring the p over, and then I just have the 1 plus I to the power of n. And then when I take the log, it'll be much cleaner, right? And so I'm going to divide both sides by p, so I get f over p is 1 plus I to the power of n. We don't have to, but it makes it much easier. Now we can take the log of both sides. So the log of f over p is the log of 1 plus I to the power of n. So the log of f over p is n times the log of 1 plus I. Right? I'm trying to solve for n, right? So I just hold n steady and I divide both sides by log of 1 plus I. I'm going to do my signature move, right? When I'm at the end, I want to solve for n, so I move it to the left-hand side because that's where I like to have what I'm solving for, right? But it's equivalent. So you get n is the log of f over p over the log of 1 plus I. Done. You've solved for n. Without knowing what f or p or I are, we can't do anything else. Cool. How about example 128? Solve 3 plus y to the x is 34 for x. Okay. 3 plus y to the x is 34. Okay. I can take the log of both sides to bring that x down. Right. You guys comfortable if I do it in one step? X times the log of 3 plus y? No way, Jose. All right. The log of 3 plus y to the x is the log of 34. That's the same as x times the log of 3 plus y. I would have just skipped from here to here. Can skip. Is the log of 34. So then, now I can divide both sides by the log of 3 plus y. So x is the log of 34 divided by the log of 3 plus y. We can't go any further because we don't know what y is. So that's good. So do all suggested exercises in section 4.1, right? Both for exponents and logs. Not for you to hand in, but for you to be able to stay on top of this stuff. Because like I said, after today, I assume that you know this and you're comfortable working with exponents and logs. Okay. Any questions? Great. I guess have a good weekend then. If you didn't get your test back yet, come grab it. I don't want them. Nice. And this.